We will now use the SPKR tree to describe the dynamic program to solve our representation extension problem. We will use one simple observation. Let's say we have our S and our T, and we have some fixed bars in between. Those are always orange. This is a rectangular representation, so S and T span a rectangle. Also, there's a bounding box for all these already represented bars. Now the observation is that the bounding box of any solution here contains the bounding box of the partial representation. But the way it contains it can be different. So if we know this part here is already fixed, but we don't know anything about all the other bars. There's an infinite number of possibilities how we can place all the other bars to get a representation of the whole thing. But if we look at it from the outside, we don't really care what happens in the interior of this. We only care what is the dimension of this box, and we only care if we can make it wider or narrower. So how many different tiles can we really have? Actually, there are only 4 types. So if we look at the two sides, here the right side is fixed because it coincides with the right side of a fixed bar, but the left side is loose because it doesn't coincide with the side of any bar. It can also be the other way around. We can have the left side fixed and the right side loose. Or we can have both fixed or both loose. So there are 4 types. And if we look at this, if we have a representation here, then this gives us one fixed part and one completely free part. And everything inside here we can freely stretch or make narrower and get different representations where no visibility is changed. So we just take everything here, scale it horizontally by some factor, and we get a different one. So if we look at it from the outside, it only matters if the sides are fixed or loose. So if we can push or draw, or we cannot. And in the recursive algorithm, we will always tell our children what type do we need. Do we need both sides to be fixed? Do we need both sides to be loose? Do we need one to be fixed, one to be loose? Depending on how the structure looks like. And to get an impression how to do this, let's just jump right into the first type of nodes, the P nodes. So let's say we have some source S, some target T, and we have a bunch of edges or components between them. Some of them here are orange, that means that some vertex inside this component is already fixed. Some of them can be black, that means they are completely free, and then there might also be this single edge here. So let's put all these fixed bars in here. And we want to find the bounding boxes for all these components and draw it. Now we don't care anymore what happens inside here, that's completely inside the component. So let's just remove it. And now since all these components are disjoint, they must be separated horizontally. So the children with prescribed bars have to occur in some given left to right order. And that means we know we have to place the whole component that corresponds to this, at least in this part. It might extend to one or both sides, depending on if we can get a fixed or loose fixed and so on representation or not. But there are some gaps in between. And those gaps we still have to fill. How can we fill them? Either with some of these non-fixed components, or we need one of them for this edge. Otherwise, we have to fill them with these components that we have here. So we have to extend some of them. And generally, all of these, they can fit inside a single gap. So if we can fill most of these gaps just by extending these green parts, then we're happy. So what we will do is that we will greedily fill the gaps by preferring to stretch the children with prescribed bars. So to fill this gap, we ask this component here, do you have a loose fixed or a loose representation? If it does, then we can fill this to the left. If it has a representation with a loose on the right, then we can fill it to the right, and so on. This one here, we don't even ask if it has a representation with loose on the right, because these parts here touch. There's no way to extend this. So here we only have to figure out, do we have a loose fixed or a fixed one? So we ask our children, can you be loose on this side? If yes, stretch it, otherwise keep it where it is. And then we have filled as many gaps as possible, and for the rest, we place these remaining components. And depending on what we're asked from the parent, either the S and T ends here, or it might end here if it has to be fixed. And the same on the right side, it can end to the right or exactly here, depending on what type of representation we want. So after this, we have to know all the valid types for the corresponding subgraphs, and then we can plug this together. What about the S nodes? Here we have a path, and inside we have components. Let's first assume that one of these vertices on the path is fixed. That means we can only make a fixed representation, because we're not allowed to have a visibility from here to here, not from here to here, and so on. So if this is loose on this side, then there is some visibility between these bars that we're not allowed to have. So it must look like this. That's already very restrictive. We can only do FF. On the other hand, if we don't have that, then again we can be loose, we can be fixed on both sides, and we can choose. And here we can clearly see the tiling. We have these rectangles above each other, we have these smaller rectangles here, so we just recursively find a representation of this. And depending on what we want, it can be fixed or loose. That depends on the type we get asked from the parent. So we have a chance to make all types. The trickiest part is handling the R nodes. So let's say we already have some representation. We will now take the endpoints of the bars and shoot a vertical segment upwards and downwards until it hits something, like this. Now we want to figure out where are these components that correspond to the edges here. This one is between 5 and T. The only part between 5 and T is exactly here, so it has to be this rectangle. Between 14 and T, this lies exactly here. It cannot span any further to the left, to the right, so it's exactly this rectangle. Between 13 and T, it's exactly this. And that way, for each of these edges, we get exactly one rectangle in the tiling that we got from that. And now the nice thing is, we have different colors and each color is a single rectangle. Can we have something like this? That we have two green rectangles, for example, so two candidates where this edge can be? No, we cannot. Because if we look at the graph, then we have some node for this, some node for this. We have some component on the outside, but this edge inside here is captured, even if there are more edges here. Then we have a cutting pair. And this is not allowed because we have an R node. This is reconnected, so this does not exist. So just from the embedding that we have for this, and from the y coordinates that we have, all these rectangles are defined. And we can stretch things, we can move things around, but we will always have exactly this embedding of the rectangles. We will always have the cyan one at the top left, to the right the blue, to the right the brown, because we have here cyan, blue, brown. Below 14 we always have green, gray, orange, like here. So just from the embedding we can read off the exact order of these rectangles. And since it's reconnected, there's a single embedding, except up to flipping things. but we can check both of these. So we have a unique tiling, we just don't know the exact dimensions. And now, if we again have some bars already inside here, then we can recursively solve all these tiles. And to do that, for each child here, or every edge here in the R node, we will want to find all types FF, FL, LF, and LL that admit a drawing. So we ask the children for each of these types, do you have a drawing for that? And then if we have that, we have to combine these types of drawings that we got. And that we do with a two-set formulation. What does that look like? Well, for every edge here, we have two variables that encode the fixed and the loose type of its tile. So we have a variable LE that's true if the left side is fixed and false if the left side is loose. With additional constraints, we can say this here has to be fixed, for example, or we can only have FL or we can only have LF, depending on what type of drawings the child admits. But then to be able to make sure that we can combine things, we need additional constraints, the consistency constraints. So let's have a look here. In this example drawing, this type here is loose, 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 loose. This here is fixed, fixed, because it has a fixed on both sides. This is fixed on the left, but loose on the right. We can, for example, take this part here and move it to the right. So this here can be loose, loose, or fixed, loose. But there are some things that we cannot do, and that's where the consistency clauses show up. If we look at the red and the yellow here, we can move this splitting line to the right and make this fixed on the left side. Or we can move it to the left and make this fixed on the right side. But we cannot have at the red one fixed right and at the yellow one fixed left. That's not possible. One of these two has to be loose. So from that we get another clause. Either this is loose or this is loose. And all these types of consistencies can be formulated with clauses that only have two literals. And then we get a two-set formulation, and that we can solve in linear time in the number of variables and clauses. The thing is, just doing this greedily, we might get a quadratic number of clauses, because we also have to fix this left to right order. But if we are careful, then we can reduce it to order of n log squared n, and that's the part we don't look at here, but it is proven in the paper by Chaplik et al. And that's all we have to do. Now for all three types of nodes, we know how to recursively ask the children for drawings and how to combine these drawings via tiling to get a drawing of this node. And then if we have done this for the root, we are done and we have drawn the whole graph.